Good morning.
Good morning, everyone. How are y'all?
Good. How are you?
Not too bad. Ready for another day of learning about cosmology and teaching about cosmology to you guys.
So I have a quick question.
Yes.
Um, and this revolves around um, just like the content of like a few of the questions that just keep all the time showing up on the test. Are they
Okay.
are the questions so that like there's some of them that are continuously showing up and they're like the same questions that we get like every single time that are like from test number like from
One or
chapters
two.
1 and
Yeah.
2,
Right.
like those are supposed to be there, right?
Yeah. Yeah.
Okay.
What those questions are the ones that students are having difficulties with, so I keep them in there. And
Okay.
they keep trying to learn it. So the moon phase questions, the motion of stars, which direction will a star be have moved after 1 hour or after 24 hours or after 23 hours 56 minutes. Those types of questions are all, as well as the ones where you have the little diagram of a nucleus and then the electron orbitals.
Mm-hmm.
Those are all fundamental astronomy questions that students don't necessarily always get that easily. So I make sure I reiterate it over and over again and hope that they'll ultimately learn it, because those are sort of some of the most fundamental ideas that I want them to leave the course with.
Okay, I was just wondering if it was like a glitch or something, and I was like, I've seen this question like 7 times now.
Exactly. Yeah, no, in fact, it gets a little more obvious because as the semester goes, I only do 10 problems on the practice tests. And
Right.
if you're taking, a certain number of questions out of chapters 1, 2, 3, and 4, uh, as the chapters that you've passed gets larger and larger, those questions become more prominent. So
Yeah.
seeming like it's way more important than it even is,
Yeah,
which it
it's like
is super important.
I never see them on my practice tests, but I always see them on like the real test. And then I go, wait a minute, hold on. I've seen this before.
Yeah, it's probably if I had my brothers, if I was a student that knew exactly what I as an instructor knows, then I would probably take practice test one as preparation for every, even practice test 1 and 2 as preparation for every test. Because, like I said, as the numbers get higher and higher, so we're now, for instance, covered chapters 1 through 14, and then we jump to some other chapters, and now we're up in 22 today. Uh, the number of chapters that have passed is getting large, so your likelihood of seeing the individual chapter 1, chapter 2, chapter 3, chapter 4 questions is lower and lower each practice test. So, ideally, just because I know what I do, me as a teacher, me as a student would suggest that I do chapter practice test 1 and practice test 2 over and over, just so I don't miss those, because those are really more important than many of the other ones. The only other ones is when we talk about the interaction of matter and light. Those questions are critical too. So I would try to find some way to find those, or just look at old test questions and make sure I know how to do them.
Okay, thank you.
You're welcome. But yeah, it's not a glitch; it's on purpose. Anybody else have any questions?
Are all the grades like put in so far for everything in lab and
Oh, absolutely not. No, in fact, I've got several students. Oops, I've got several students that have not turned in various labs. So I sort of wait on students turning in labs before I grade them. So a lot of those aren't graded. Students have turned in Astro points. I will probably, maybe even this week, go ahead and start getting rid of those assignments. In other words, making the grades appear. So you should be able to ultimately look in your grade book into how many Astro points you turned in. Plus, I got to go through the old files and see how many attendances y'all have made and how many attendances you haven't made, or how many you just were here for a couple of minutes and then left. So that'll add more Astro points to your system. And then, like I said, the labs, I just need to start doing that. And I'm just going to have to take everybody that didn't turn in a particular lab and dock them a buttload of points for not turning it in yet. Once that starts happening, then all the grades will make more sense. Just remember, your grade really is, as long as you get that 1,500 points, your grade is just your average of your tests. So if you look at the online test average, or actually just the course average that it says in the thing, that it's actually taking account of the fact that the midterm is a higher percentage than the online test, and it's actually adding all those. So that really is your score. Because the Astro points really don't matter unless, like I said, unless you screw up and get less than 1,500, then it's going to be 10 points lower. Or if you really excel and get 2,500 points higher, or 2,500 points or higher, I should say, then you're going to add.
Probably have to get 1,200 points.
What's that?
Probably have to get 1,200.
1,200, you lose 10 points.
I thought it was minimum of 1,200. That's what it says.
It might be. I could be misstating that because, like I said, I change in different classes. So my syllabus might say 1,200, in which case nothing happens negatively. But if my syllabus says 1,500, which is what I thought I remembered correctly, then yeah, it would be 1,500. But literally, like I've had to take points off, and I hate it for students that are 3 points shy of the 1,500, or 1,200, whatever it happens to be. So. You should check your syllabus to make sure I'm right about, or you're right, or I'm right about that, because I'd hate for you to be 300 points shy because you misread or misunderstood the syllabus.
So this week, I believe the syllabus does say 1,200. I think I checked this weekend, but
I like that better.
This upcoming weekend coming up, we'll be able to like detect how many Astro points we have.
Well, you should know that already. I suggested everybody keep a record of that. But you should be able to, once I get all those grades done, you should be able to look at it and see what's there. You should also be able to look at a particular column, or in your case, rows in a grade book, and see which Astro points you turned in that I haven't given you credit for. And then you
right. But it also works for the attendance too. Exactly. So like all of that will be put in this weekend, and then all the other Astro points.
Yep. Okay. So I would advise you guys, I'm the only one that even takes any time to put the Astro points in the grade book. So, among my faculty that work at TCC, and I would advise that even though I'm behind on doing that kind of grading and stuff, I'm still way more lenient and helpful than other faculty, especially at other schools. So I would highly recommend you guys start keeping, taking control of your own life and keeping records of everything you do, at least till the course is over. And you are happy with your grade, because at the end I found a lot of people, teachers that have graded courses and didn't do them properly, and because of my ability to reproduce my grades that I've made, I was able to change my grade, and there's nothing they can do about it, because that's what the syllabus is. It's a contract between you and I have to stick to it just like you guys do. So if y'all are sort of floating through life like a jellyfish on a current, and you miss the, not keeping track of how many Astro points you turned in, and you're shooting yourself in the foot, and it could come back to bite you later. So I would definitely start recommending you keep a file listing, at least, if not actually keeping a separate copy, a file in your actual computer, a virtual file with everything you turned in and how many points it's supposed to be in a running total. So just do that, because like I said, not all instructors are nice, and well, I shouldn't say that they're mean, but I'm just saying that not all of them work so hard to make sure you guys know what's been turned in. That's the whole reason I took several hours to make all those columns in our grade book, is so that you guys can at least see where you've turned one in, and then just go up and say, oh, okay, well, that's supposed to be this worth, and then you just add them up. So not to pick on you guys, it's just like I said, I want you guys to go out, and just like I want for my own daughters, I want them to go out and be independent enough that they can challenge an instructor when an instructor makes a mistake, and do so politely, but still challenge them. If the instructor makes a mistake, you need to challenge the instructor and say, hey, this is a problem. I have a B, not a C. Okay. All right. Well, that's about it. Anybody else have any other questions? Yeah, so hopefully this Thursday, Friday, and Saturday, I have time to do some more grading stuff, and that would be awesome. And I will, as I do such things, I'll let you guys know. So if I get a big number of grades done, I'll email you guys. If I only do 1 or 2 columns, I'm not going to let you know. But if I get several done, I'll go ahead and send you an email and let you know. All right, well, let's go ahead and get started on chapter 22, which is on cosmology. I'm going to start with sharing the screen of our PowerPoint. Here's the PowerPoint. And I'm going to then begin playing the role of a good teacher by reading you the learning goals for the chapter. So, chapter 22, Cosmology. Learning goals. By the end of the chapter, you should be able to, 1, explain how mass within the universe and the gravitational force it produces affect the history, shape, and fate of the universe. Notice the use of the word affect there, just for a everyday education thing. It's very rarely that you use affect, A-F-F-E-C-T, but this is exactly the time that you do. Explain how mass within the universe and the gravitational force it produces affect the history, shape, and fate of the universe. Learning goal 2, describe the evidence for the accelerating expansion of the universe. I was mentioning that last time. Perlmutter and Reese, and now I've forgotten the other guy's name. Let's say Schmidt. Schmidt, that's it. Yeah, maybe we'll say that. Won the Nobel Prize for showing that not only is the universe expanding, but it's in fact accelerating. So that's a pretty big deal. I'm sort of stalling you guys right now so I can look up that third guy's name that I made a point to point out, since that in the last video I said I just can't remember their names and felt like a jerk for doing it. Yep, not going to happen this time, evidently. Anybody know it? Perlmutter and Andy Rice, I think R-E-I-S or R-E-R-I-E-S or something. Anyways, they won the Nobel Prize for showing that the universe is not only expanding, but rather expanding and accelerating, which is the origins of our ideas of dark energy. Learning goal 3 is describe the early period of expansion of the universe known as inflation. So that's an attempt to solve the horizon problem and the flatness problem of cosmology. So that's another important thing we should know. And we should also know, of course, that was the idea of it was introduced by MIT physicist Alan Guth. So I just wanted to make sure you were aware of that. That's a recent guy. He was in the movie Beyond the Big Bang, or the Big Bang and Beyond, what it is, the season finale of season 1 of the Universe series, which again, probably now would be a good time for you guys to watch it, just to recap what you've learned. And then finally, learning goal 4, explain how the events that occurred in the earliest moments of the universe are related to the forces that operate in the modern universe. So those are the 4 learning goals. Hopefully you guys will try to take that seriously by actually writing those things down, maybe even turning them into questions, and then answering those questions in really thick, robust, well-documented, well supported with experimental evidence answers. So that's sort of the holy grail for each chapter, is to actually do that with the actual learning goals of each chapter. And oh, there it is. Yeah, I was right. It's Brian Schmidt. So it's Saul Perlmutter, Brian P. Schmidt, and Adam G. Rice. And I thought it was Andrew, but it's Adam G. Rice. Were the people that won the Nobel Prize for discovering that not only is the universe expanding, but its expansion is accelerating. So that's kind of cool. Now, from that, let's get into chapter 22. So here's a really cool picture. This is MGC 2376 or something. I can't remember the numbers, but you can see it as the opening picture in your chapter 22. And what you see is, anybody recall what type of galaxy that is? You got 3 choices and then subsets within a couple of choices. So is it elliptical, is it irregular, or is it spiral?
Barred spiral.
Very good. So yes, you even went beyond. It is a spiral, and in fact, it's a barred type spiral. You can see a single bar going across here. But see this one star, how much light it puts out? It looks really, really bright compared to almost everything else, except for maybe some of these more foreground stars. This is a star going type 1A supernova. So that's, again, what we use many times to figure out distances. And it turns out those are the best things to use when we're trying to track down the expansion of the universe and whether it's changing. In other words, is the Hubble constant, that 70 kilometers per second per megaparsec, is that a constant? If that's a constant, then automatically 1 over it would give us 13.8 billion years roughly, which is the age of the universe. But if the Hubble constant is increasing with time, then it would have been lower earlier and it's going to be higher later. So you get a different time for the creation of the universe. And if it's actually decreasing in time, you get a different age as well. So that's what we're leaning towards when we're talking about using type 1A supernovas to detect the expansion of the universe. As I told you before, cosmology involves the study of the universe, its future, And it's on such a scale that individual galaxies are considered point particles. So it really is an impressively large scale that you study when you're studying cosmology. The universe is expanding now. It seems to have been expanding forever. Future expansion could be faster or slower. That depends on some very specific factors. And we'll discuss those factors as well. And expansion could halt and reverse. I've got someone hitting more here. Someone chatted, oh yeah, thank you. Someone's offering me the information regarding Saul Perlmutter from Lawrence Berkeley National Laboratory, Brian Schmidt, and University of California, and Brian Schmidt from Australian National University, and Adam Rees from Johns Hopkins. So yes, thank you for that. The future expansion, like I say, could be faster or slower. Again, that depends on some parameters we'll learn about in this chapter. Expansion could halt and reverse. Again, same parameters. Fate depends on how much matter, and I'm talking the fate of the universe, depends on how much matter there is in the universe. And gravity from ordinary and dark matter slows the expansion. So you can imagine gravity from dark matter and gravity from matter both act as a pulling force. Remember, gravitation is only a attractive force. There's no repulsive gravity. So every time you find any new mass, whether it be dark or regular mass, then you know for a fact that's going to tend to pull other things in the universe, since it has an infinite range, try to pull them together. Dark energy, on the other hand, seems to be in opposition to that and actually seems to be pushing away things. So the big question is there enough gravity to halt expansion? And that's sort of the major question of this chapter. And of course, we're also exposing you to some of the ideas that people are using to address these questions. The fate of the universe is expanding. The harder it is to stop it will make it contract. So in other words, if it's expanding, well, we know it's expanding, but while it expands, if the mass is really, really large, then that mass will be causing it to slow down until it comes to a stop. Maybe it just barely comes to a stop at an infinite amount of time, in which case it's forever expanding. It could also expand forever and get larger and larger and larger because there's not enough matter causing enough gravity to slow it. The more mass there is, the more gravity there is to halt the expansion. And then we define a critical density, and this critical density is called omega matter. That's the omega letter that you see down there with the lowercase m as a subscript. They call that omega matter. And it's really the ratio of the critical density divided by the density of the universe. So the critical density is density needed to almost slow the universe to a stop but not reverse it is called the critical density. So if the universe's mass density is equal to the critical density, then the universe will expand forever, but just come to a stop as time reaches infinity. The omega matter, like I said, is the ratio of mass density of the universe to the critical density. So like I said, if the mass density of the universe is the critical density, then you get 1. If the mass density of the universe is less, you get less than 1. If the mass density is larger, then you get a number greater than 1. And that number actually is kind of funny. Let me stop sharing the screen for a second. And now let me pull up something that I like showing my students. And I meant to pull it up earlier, but I didn't get time. So I'm going to do a search for it. I'm getting there. Hold on a second. So it looks like it's not going to be as easy to find as I would like to. Anyways, I should have done that beforehand. I didn't, so I'll just have to allow you to look for it yourself. Let me go ahead and go back to sharing the screen. But what I was going to tell you was there's an episode of The Simpsons where Homer learns about Thomas Edison. He gets really excited because Thomas Edison's an inventor, and he really wants to be, an inventor just because he, was so impressed with Thomas Edison. And he comes up with all these inventions trying to get rich, one of which is a makeup gun, which is quite funny because Marge says, hey, Homer says, hey, Marge, look at me. And she looks at him. He's got a double barrel shotgun pointing like right at her face this close. And he said, I'm going to save you time. He goes to pull the trigger and she ducks. About that time, it blows an image of a woman's face and makeup all on the background wall. And she's like, oh, Homer, I think you've got that sent to whore. But it's kind of a funny story that way. But later on in the episode, it shows that he goes down to his basement and he's working on some invention. And what he's got written on the board is omega, just like we use in cosmology, the symbol that I just showed you. He's got that omega greater than 1, and then the house explodes. And then he comes down later and the board's been erased. He's got omega less than 1 and the house implodes, which is really kind of cool because the Simpsons authors are actually notoriously, 1, educated, but 2, they're also notoriously gifted in math and science. They've had people that are literally 1 degree of separation from Nobel laureates in physics and math and stuff of that sort. So it's kind of cool that the Simpsons actually had that video. So check that video out if you ever get that episode where Homer Simpson wants to become an inventor after learning about Thomas Edison. It's got a lot of funny parts, but the cool part is, like I said, it has that omega literally on the board for you to see. And in fact, if you read the Mathematics of the Simpsons by Simon Singh, you'll find a lot of other cool stories like that. So let's go back to sharing. I just wanted to make that relevant to at least to something that I love, which is The Simpsons. You'll see other stuff like that on other shows. For instance, Futurama has a lot of the same writers, so they do stuff like that as well. I haven't seen as much with like King of the Hill or Bob's Burgers, but still there's some pretty relevant stuff that they put in those. In fact, Simpsons have a ton of cultural statements or analogies and stuff like that, just with not only our culture but cultures in general as well as pop culture. So all right, let's go ahead and get back. So we were talking about the omega m, which I said was the mass density of the universe divided by the critical density. Alexander Friedman actually already calculated the critical density. He did that with Einstein's equations and some expressions we know from cosmology. And this was shortly after Einstein's general theory of relativity. He's the guy that I told you that first did some idea suggesting that Einstein's equations were telling us the universe was expanding. And then George Lemaitre came out and did it again, but probably without the knowledge of Alexander Friedman's work because he was in Russia at the time. But anyways, the general theory of relativity did predict this potential of the universe to be expanding or contracting dependent on this critical matter. Alexander Friedman did a calculation of that. Your book has it in Working It Out, and it's about 6 hydrogen nuclei per cubic meter in space. So if outer space, all of space in the entire universe, has on average the mass of one hydrogen atom, the mass of almost 6 hydrogen atoms, it's like 5.7 of them, in every cubic meter of space on average, then we'll be at the critical density, and omega m will be exactly equal to 1. So far, it's looking like omega matter, omega m is also call it, is more like 0.2 to 0.3. Okay, so that's taking into account not only matter, but dark matter. The matter actually was around 0.2. The dark matter was about 10 times more, so that the matter was 0.02 omega matter. And then the dark matter is about 10 times as prevalent, so it ends up going up to about 0.2 instead of 0.02. So, fate, if only matter is involved, here it is. So if only matter involved in the critical density is in fact equal, or the omega matter is equal to the critical density, which is 1, and I really mean the density is equal to the critical density, omega matter is equal to 1. This is what happens, and you can see basically the scale factor getting larger and larger and larger, but the rate at which it's getting larger is getting smaller and smaller and smaller. And eventually it'll sort of try to level off, but it'll never quite reach level. It's like asymptotically approaching level. So at infinite amount of time, it will just reach horizontal. So it's never going to reach horizontal. If the omega matter is less than 1, okay, that means that the mass of the universe is, the density of the universe is less than the critical density, then it will not only expand forever, but the expansion won't even necessarily slow down. Okay. And if the omega matter is greater than 1, meaning the density of the universe is greater than the critical density, then the universe will expand, 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 reach some maximum, and then start to contract, 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 and then it'll end up in what we call a big crunch, where all the matter will come together. People have hypothesized this, and in fact, I came up with this idea when I think it was in 4th grade. Having, not being weighted down with any of the knowledge of actual facts, I learned about this idea of the universe expanding and contracting. And I just imagined that if it actually did contract, it might just start back over and do it all over again. And that would, quote unquote, explain deja vu and stuff like that. Of course, that was, me being ignorant of all the science and facts, but just coming up with pure imagination, what could happen. It turns out that's actually something that other people have considered as well, and I'm sure some of you have. So if omega matter is 1, then it will actually have the critical density, and the universe will slow asymptotically to a stop. Yeah, are y'all familiar with that word, asymptotic?
No.
Okay, so the asymptotic word is a mathematical one. They used it in Revenge of the Nerds. They were out on the beach, and he said, imagine an asymptotic line extended outward or something like that. So you can also think of it as that old adage where you say, if you want to go to a certain distance, maybe you want to run a 24-mile marathon or something like that, you can start by just going halfway. And then you can go halfway again, and then you can go the halfway again, keep dividing up what's left by half. Well, if you do that, you technically will never finish. You would just get closer and closer to the 24 miles, and in an infinite amount of time, you will get infinitely close, but you're not quite there yet. That's asymptotically. So as you get infinitely close to something.
Asymptotes, right?
Yeah, exactly, like asymptotes from hyperbolas and algebra and stuff like that. Yep. Like if you ever seen the graph of y equals 1 over x, it has those two curves that go like this, and there's an asymptote horizontally at y equals 0, because you cannot make an x such that 1 over x is actually 0. And there's also one at x equals 0, because obviously you can't have a 0 in the denominator. But yeah, that's asymptotically that we're talking about. If lambda m, or omega m, or omega matter is less than 1, the expansion will go on forever. The universe will slow a little from gravity, but it will continue to go. And in ordinary stars and galaxies, when we just look at stars and galaxies, like I told you, omega matter is about 0.02. If you add 10 times as much as that, you obviously are going to make it around 0.2. It's actually a little bit more, of course, but that would be the entire matter plus dark matter. And if you go ahead and take into consideration some of the other things that we've put together, basically stuff that we don't see that's not necessarily dark matter, but it's just hard to account for, which is, atoms and molecules in the interstellar gas and stuff like that, then we get up to about 0.3 for omega matter. So omega matter is clearly way less than 1. So what we see is omega matter being clearly less than 1 means that the universe will expand forever. We're not going to get a big crunch, and we're probably not even going to slow down. Okay. So at the end of the 20th century, this is the actual graph that Perlmutter, Schmidt, and Rees actually put together. Basically, what they realized is it's really hard to get a consistent representation of redshift from just galaxies in general. So they use type 1a supernovas predominantly, and they made plots of it, redshift versus relative brightness. And then they made a plot for the line of basically this bluish, darkest colored line that you see there is a plot for the redshift increasing. In other words, for the universe to actually increase in its speed of expansion is what that darkest blue line follows. The next one is maybe a little less severe increasing, And then the green line is a little less severe still. The orange line is sort of, if it was a constant, actually it's somewhere between the orange line and the green line. And then the red line is if it was slowing down. When they did an actual curve fit, the line of best fit actually suggested the universe was in fact increasing in its expansion rate. So in the past, the universe was accelerating, or excuse me, was expanding slower than it is now. And now it's expanding even faster. So that's a really big deal. And in order to do that, you got to be fighting against gravity, because gravity is still infinitely long reaching force, just like the electric force reaches infinitely far away. But because most matter is neutral, that one's not a big deal. So we don't worry too much about it. But with gravity, we do worry about it. It's always attractive. It always tries to slow things down. But in this case, we're finding that despite that gravitational pull trying to slow the universe down, there's some other kind of energy in our system, that is the universe, that's pushing the galaxy to, or the universe to expand even faster. We labeled that dark energy, and now we have the wonderful idea of dark energy. And dark energy seems to not necessarily be as prevalent as dark matter, but it's still going to be very, very large fraction, way more than regular matter. Again, if you relate the energy to matter with MC squared. So the observations of type 1a supernova and high redshift galaxies show that the expansion was smaller in the past and is larger now. The expansion is accelerating, not slowing down. This acceleration indicates that there's a type of energy in the universe that pushes on space, acting against gravity. Now, remember, I told you that Einstein introduced his cosmological constant, which is that triangle with a missing leg that you see there. It's a subscript on the omega. So that is, like I said last time, it's a lambda. It's a capital lambda. And that's the symbol we use for Einstein's cosmological constant. And basically what Einstein saw was that his general theory of relativity was predicting that based on the amount of mass in the universe could be expanding, could be expanding or contracting. He knew the evidence suggested the universe was static and that it wasn't moving. So he put in that fudge factor that would allow him to, basically dial that fudge factor just right so that we could later determine, make sure that the universe stays static. So that's why he put it in there, is just to make it fit the data that we knew at the time. And he called it his greatest blunder. And in fact, had he not done it, if he left that off of there, he could have left open the question that the universe may in fact be expanding or may in fact be contracting. And he might have even been able to do a calculation to see which one it was, and got yet another Nobel Prize for that prediction. Instead, he chose to, in his words, in exchange for him being such a pain in the butt to experts, the universe or God got back with him by making him an expert, so that he screwed up just like the other ones did. So yeah, he called this lambda the greatest blunder of his life. What we now do is we say, okay, well, there's this lambda that is the cosmological constant, and we let that dictate basically how the universe is expanding. So the lambda is in fact a symbol that we use to represent the dark energy. And then its effect on the mass density of the universe we call omega lambda. So omega gamma. And omega gamma is really the cosmological constant part of the omega matter. So you take omega matter and omega lambda, those two combined give you a total omega. And if that were one, then you've got different sets of things that can happen, whether the universe expands forever, expands, then contracts, and so on and so forth. So we're just back to where we are because we have to add in this other part, dark energy. Okay. So dark energy changes the universe's possible fate, since it's more difficult for gravity to reverse the expansion. So if we actually had no such thing as dark matter, then again, just taking omega lambda, not omega lambda and omega matter, just taking that into consideration, then clearly the universe would expand, reach a maximum, and then contract to zero. If, however, the omega lambda was greater than zero, again, ignoring the lambda matter right now, we would actually have it expand and contract eventually as well, maybe in a longer period of time. But if it was markedly greater than 0, we could actually have the omega matter doing enough to act, or excuse me, the omega lambda doing enough to actually cause it to expand and continue to expand, or it could be expanding, continuing to expand, or it could be continuing to expand and expand even faster. So that's what they're showing is, again, that scale factor of the universe, how much the universe has changed its size uh, since 13.8 billion years ago or something. So that's what they're showing with that. Astronomers use omega, the very last letter in the Greek alphabet, to discuss the densities and the ultimate fate of the universe. We can learn about omega gamma, or excuse me, omega lambda, using supernova, galaxy clusters, or the cosmic microwave background radiation. It appears right now, experimentally, our best estimates are that omega lambda is 0.7 and omega matter is 0.3. So the two of them add up to give you 1, which means one, the universe is actually flat, which is awesome. And very unlikely that the universe would be flat now unless it was really, really pristinely flat in the very beginning. But the universe will accelerate and will expand forever as long as these facts stay the same. Because remember, at the end of the day, the overall omega is 1 now. So since the overall omega is 1, that means it's going to basically expand forever. Here's scenarios for a collapsing universe, for a critical density universe, for a coasting universe where it expands and continues to expand forever, and then for an accelerating universe. This horizontal slice here is what we see right now. And what they're showing you is how if the universe was accelerating, the distant past would have been farther back. So the universe would be older than 13.8 billion years old. And would expand forever. If we're in a coasting universe where it's expanding at the same rate more or less forever, then the universe probably is right about 13.8 billion years ago. If the universe is actually slowing down or is right at the critical density where it'll expand forever but never really slow down, then we're going to get a slightly shorter distance back to the Big Bang, which would be less than 13.8 billion years, or we could have, again, way less than 1, in which case you get a collapsing universe, and that results in a little bit shorter universe still. So where basically matter takes over and causes everything to come back to a small space, that's called the Big Crunch. If the dark energy effect increases with time, the entire universe will be ripped apart and called the Big Rip. So what we mean by that is the dark energy of the universe will be so significant that it's not only going to do what it is right now, which is causing the space between the galaxies to expand and speed up, it'll eventually get so strong that it can actually expand the galaxies themselves. In other words, the individual stars and interstellar gases and dust and black holes and stuff that are in a galaxy, the gravity connecting them to one another and holding them in that structure will actually be overwhelmed by the dark energy, and the galaxies will break up. And then if you go further still, the individual gravity that holds together stars will break apart the actual stars and the planets, and then eventually it'll get so bad that the individual atoms will be their strength, their Coulomb force that holds, for instance, the electrons to the nuclei, that will be overcome and atoms will fall apart, and then they'll continue further still, and the strong nuclear force that holds the protons and neutrons together will be overcome, and you'll basically just have the universe as a big ginormous space with a bunch of independent particles, elementary particles that have been completely ripped apart. So it'll be basically gluons, quarks, W0, W plus, and Z particles, and photons and electrons. So pretty much it. Now, right now, what we're looking at is it's more likely that the data are consistent with dark energy, which will end in a cold, dark, dead universe called the Big Chill. And in fact, what's going to happen is long before, well, even if we humans were like, say, vampires and could live forever or whatever, we would eventually reach a big chill where basically everything comes apart and all the sources of energy are gone. Since the sources of energy are gone, obviously the universe will start to reach 0 Kelvin. And there's no real, since they're so spread apart, there's no way to interact to cause other things to warm it up. That's the Big Chill. So again, another uplifting topic from Mr. Younger in his astronomy class. Luckily, we're talking tens of billions, if not hundreds of billions, if not thousands of billions of years from now. So don't worry too much about it. The universe's age does depend on the acceleration. Without acceleration, the age is its age is less than the Hubble time. So if it's not accelerating, the Hubble time, which is 13.8 billion years ago, without acceleration, the age would actually be younger than 13.8. With acceleration, his age is greater than the Hubble time. So we think, maybe 13.8 is a little short. That's the Hubble time being too short amount of time, meaning the universe is younger than 13.8 billion years, is a bit problematic experimentally. So we more or less throw this second bullet point idea away because we have globular clusters and stuff of that, star clusters, whose age is right around 13.5 billion years. So it can't get much shorter than 13.8 for us to have reality match it. So most scientists are in agreement that the universe is probably at least 13.7, 13.8 billion years old. Observations show that expansion has accelerated. So the Hubble time is a minimum age. So we think the universe, in fact, is at least 13.7, 13.8 billion years, but it may in fact be slightly more due to the observation, due to the acceleration. Now, the acceleration could have been very, very slow and then recently turned up, or it could be basically the same rate all the time, or it could be really, really fast and it's slowing down. There's all sorts of ways this can change. And we don't really know enough to say what it was, but the key point is to understand that if the universe is accelerating in its expansion, then we might not be exactly correct about the age of the universe. The shape of the universe is the other big deal. And it turns out if the omega matter plus omega lambda adds to give you 1, then you get a flat universe. And this is a flat universe. Now, it's not flat in the sense that every little spot you get to will be flat. For several hundreds, well, actually for several thousands of years, humans thought the Earth was flat. And you can walk across the Earth, even, as a man walking 6,000, 8,000, 10,000 years ago. If you're walking across the Earth, you can see that clearly the Earth is not flat. You see mountains, you see valleys, you see holes, all sorts of stuff. In that sense, it's not flat. And in that sense, the universe is not flat. Obviously, we're going to have dimples all over it. Gravity, general relativity taught us that matter actually causes space-time to warp. So you have little dimples in it as a result of masses, and that is what we know of as gravity. It's not really a force so much as it's a shape of space forcing things to move in non-straight lines. But if you can take a spot maybe 10 or 10,000 megaparsecs away and another 10,000 megaparsecs away from that and another 10,000 megaparsecs away from those, you could make an equilateral triangle in space that literally is tens of thousands of megaparsecs across. And if you measured those interior angles and got 180, you would be pretty confident that the space of our universe is flat. And that's more or less what we believe now is the universe is flat. We haven't done those super cool experiments where we've got things stationed thousands of megaparsecs away, but all our evidence that we do have does suggest that the universe is flat. It could be an open universe. In fact, if the omega matter plus omega lambda was less than 1, it would be an open universe, and that's more like a saddle. So you can imagine it's those of you who've had even high school algebra 2, you know about parabolas. So we're thinking of a parabola going this way, and then it's got parabolas coming off of it going this way, okay? And making out that shape, it's like a saddle, a horse saddle that goes on forever, infinitely high up, infinitely high up, infinitely far down, infinitely far down. That's an open geometry. And that actually produces triangles that have angles less than 180 and circumference that's greater than 2 pi r. But if the other extreme is the case, which is omega matter plus omega lambda is greater than 1, then you have a closed universe and it's finite instead of infinite. And that would be like a sphere. Okay, it's finite in that you can eventually go one particular direction and come back and run back into yourself. And you probably should know this already. Clearly, the sum of angles in a triangle on the surface of the Earth is greater than 180, because you can imagine walking down along the prime meridian from the North Pole to the equator, and then hanging a left, left along the equator. And when you hang that left along the equator, that's a 90-degree angle right there. And then you go up to say 90 degrees longitude, and now we'll call it east longitude, and then you take a left again, that's another 90-degree angle, and you will arrive back at the North Pole with a 90-degree angle separating the two lines that you left the North Pole and arrived at the North Pole with. And therefore your angle inside of your triangle would be 90 plus 90 plus 90, which is in fact 270. So it can be quite a bit larger than 180. Okay, so just if you forget which one's which, just remember closed is a sphere like us, and that has angles greater than 180. And because you can always imagine doing that walking from the North Pole on the prime meridian to the equator to the 90th longitude and back up. So the combination of omega mass and omega lambda is very close to 1. Why? Well, this is called the flatness problem. So when the universe is expanding, something weird happens basically. Any little fluctuations that you see in the universe are going to be blown up hugely and look really, really obvious as the universe expands. The fact that the universe is super flat right now suggests that it must have been really, 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 really flat in the past. And that's called the flatness problem. And that has to be consistent with maybe in the early universe, when the universe was first created, that omega mass and omega lambda was 1 to maybe 10,000 decimal places. It was 1.000000, where there's maybe 10,000 zeros after or something. And I might be slightly exaggerating on the numbers, but the main thing is know that it's a lot of decimal places before you get to something other than 0. And that would be consistent with right now the universe being 1 followed by maybe 3 zeros. Okay, and that's what we're seeing right now, is probably the 1 followed by 2 or 3 zeros is what our universe is telling us about the flatness right now. Now, the cosmic microwave background radiation also provides us with another problem. Specifically, remember I mentioned last time about that speckled robin's egg, and I pointed out to you that the blue, the darkest of the blue, was sort of the coldest, and the brightest of the orange, or the most intense of the orange, was in fact the hottest areas, and that the hottest area compared to the coldest area differed only by basically like on the order of 0.0000001 Kelvin. Okay, that's a really big deal. The temperatures being 1 in 100,000th variations is an extremely small thing, and the same thing makes it, or that issue makes it another problem, not unlike the flatness problem, because when the universe is expanding at the microscopic level, when the universe is roughly the size of an atom or a nucleus, or even smaller, say, quantum mechanics dictates that the universe is not very smooth at that end, because we know when we zoom into a really, really small area on the order of the size of nuclei and even smaller, there's a constant creation of particles and antiparticles going on all the time, and it's quite bubbly and jacked up. That would cause fluctuations in temperature from one location to another, and those fluctuations in temperature, once the universe expanded, should have actually shown huge differences in temperature after the expansion, but they don't. And the expansion has created a universe so large that it really didn't have enough time for the temperature to equilibrate across the entire spectrum of the cosmic microwave background radiation. So that gives us what we call the horizon problem. It appears as if the temperature has been affected by things that are beyond has been able to affect things beyond our horizon. In other words, things at our temperature, at our location, were able to be communicated way beyond our horizon, which is more or less how far we can reach by traveling at the speed of light, so that the universe actually doesn't have a huge fluctuation in temperature. And we've got to explain that. That's why the speckled robin egg is such a big deal. Well, Alan Guth suggested an answer to this, and it's not. I mean, it's a big deal, and they rightfully make a big deal about him coming up with the idea. But it basically just says early in the universe there was something called inflation. That inflation would have caused the universe to basically grow from the size. If you want to talk scale, you can say the size of a grain of sand to the size of the observable universe is about the range of change in size that it went through. So it took the universe, which you could imagine as being about the size of a grain of sand early on, and expanded it till it was about the size of the observable universe now, which is basically a sphere whose radius is 13.8 billion light years. But it did so in well under a second or something like that. So it's really traveling in some sense at greater than the speed of light. But that's not really violating relativity for many reasons. One of which is that this is space expanding, not things actually moving through space. So that's the explanation that they give. So what they're saying is basically, hey, because of inflation, whoa. Sorry about that. I don't know what just happened. What they're saying is because of inflation, the universe expanded so quickly that the temperature that was everywhere in the universe went with the expansion and made every single part of the universe roughly the same temperature all over it. So that's what expansion is, and it's really hard to test, but we have ways of testing it, and some of the results are coming back that it seems to be accurate. But it's not, like I said, it's not really well defined. Guth didn't suggest a mechanism of physics that would make it happen. He just said maybe this happened, and it was a really big deal. Okay, so in order for that to happen, and for us to understand it, you need some understanding of the forces of nature. There used to be 5 fundamental forces. There was gravity, there was the electric force, there was the magnetic force, and then there was the electric force, gravity, magnetic force. Then there was a strong nuclear force, and then there was a weak nuclear force. And of course, we were thrust upon us the idea of a strong nuclear force when we found out the nucleus was made up of protons and neutrons. And then later on, Enrico Fermi basically said that there had to be a weak nuclear force to explain the beta decay. And that then gave us the fifth force. Well, Maxwell comes along in the 1800s and basically shows through his equations that electricity and magnetism are just 2 sides of the same coin. So we now talk about electromagnetic force, and it reduced it to 4. Then Sheldon Glashow, Abdul Salam, and Stephen Weinberg got together, and I shouldn't say got together. They actually all 3 of them independently came up with basically the standard model, are the electroweak force, and it's actually the beginning of the standard model. So they actually unified the weak nuclear force with the electromagnetic force, showing in fact that the electromagnetic force and the weak force are really 2 sides of the same coin. Okay, and it's only at certain energy differences that you can tell the difference between the electroweak force and the electromagnetic force. Later on, working further on the standard model, people like Sheldon Glashow, Salam, and Weinberg, they all contributed to, as well as many other people, contributed to integrating the strong nuclear force with that. And that's what the standard model is. The standard model of physics basically shows that the strong nuclear force, the electromagnetic force, and the weak nuclear force are all different sides of the same coin. And we're really trying to integrate gravity with that. But you can see the relative strengths here. Notice the nuclear force is the strongest of all of them, the strong nuclear forces. Then the next strongest is the electromagnetic force. Then the next strongest is the weak nuclear force. And then way behind that, 10 with or 0 followed by, or a decimal place followed by 38 zeros, essentially, is how much weaker gravity is than the strong nuclear force. We have not been able to integrate the gravitational force with these other 3 to show that, for instance, gravitational force is just another side of a coin that includes these first 3 forces. Attempts to do that are grand unified theories called GUTS, G-U-Ts, theories of everything called TOEs, T-O-Es, And there's candidates for certain particles that come out of that can explain things like dark matter and dark energy. We talked before about WIMPs and machos. So WIMPs are weakly interacting massive particles, and machos are massive, massive. I can't remember what machos are. Anyways, but basically they're massive particles interacting as well. So we've got all these other ideas that help us further understand the universe, but we're no longer able to just stay in the cosmological realm, studying, galaxies as point-like objects. In order to understand the big cosmology, we'll ultimately have to understand the very small as well, which is why we're to the fundamental forces, guts and toes and stuff like that. So we actually have to understand all that stuff, and each force concerns a different process. In fact, when you talk about the electroweak theory and the standard model, which basically says those first three forces are the same, we no longer see them as forces. As I was telling you last time, you can see, for instance, two protons being separated from each other as being a result of the Coulomb force, causing them to repel, or you can see them as if one of the protons shot a photon out at the other proton. That recoil of that shooting of the photon caused the proton to actually move away from the other proton, and then hitting the other proton made that other proton move away. And that is more or less the quantum electrodynamic idea, is that an exchange of particles causes what looks like a force. And the exchange particles in that force, in the electromagnetic force, is the photon. The exchange particle in the strong nuclear force is the gluon. And as I hinted at earlier, the exchange particle for the weak nuclear force is the W plus, the W minus, and the Z0 particle. We have not found, although we'd probably call it a graviton, we have not found a way to treat gravity as an exchange of particles. And if we were able to, or if you were able to, you would most certainly win a Nobel Prize. That would be really, really cool. That was my long-term goals before I realized that I was a perfectly average human being. So anyways, so here's the actual images you can think about a proton being attracted to an electron. The electron comes flying around, gets attracted. The way they would see that is basically an exchange of particles between the proton and electron that actually causes the electron to move closer to it. It's really hard to see this in the case where they're moving together, but it's easy to see it when the cases where they're moving apart, which is what I told you about earlier. So I told you quantum electrodynamics, QED, is the quantum mechanical description of electricity and magnetism. The quantum description of the strong nuclear force is called quantum chromodynamics, which you might recall the chromos meaning colors. So there's actually sort of color particles that play a key role in here, specifically quarks. The quarks are are charmed and stuff like that. And then the gluons, of course, hold the particles together. The ideas of QED and the weak nuclear force are combined into the electroweak theory. That was what Glasgow, Weinberg, and Salam did, was introduce electroweak theory, and then continue to work on until what we now have is the inclusion of the quantum chromodynamics with the electroweak theory to make the strong standard model of physics. So it turns out, this is what I was talking about at the microscopic level, space being bubbly, not smooth, which is really a problem for general relativity. But basically, at any random time, the vacuum, meaning literally a literal vacuum, there's no particles whatsoever in existence in this small portion of space. Maybe it's the size of a die, like singular of dice. So maybe it's that big. In that area, there is going to be the creation spontaneously of a electron and positron. So an electron and its antiparticle, the positron, can spontaneously be created. And as long as that energy, that violation that occurred, conservation of energy has been violated if you create conservation of energy and mass for that matter, has been violated if you create these things out of nothingness, as long as that nothingness doesn't last any longer than the energy divided by Planck's constant over 2 pi, then you haven't violated conservation of energy according to quantum mechanics. So things will bubble out of emptiness and make an electron and positron, or spontaneously an electron and positron can be flying around and spontaneously run into each other. Since they're antiparticles, they can create X-ray or gamma ray photons. Or gamma ray photons can come together and create electrons and positrons. So there's 3 ways I just chronicled for you of electrons and positrons being created, some of which are just, by the way, we've seen all of these, but some of which are just, particles existing and then changing form for no reason. And then other ones are just something happening out of sheer nothingness, which is the first example I talked about. So pairs of particles and antiparticles were created and annihilated in the early universe through pair production. There's some reason, and we don't know what it is, but there's some reason that we ended up having a universe that's made mostly of matter as opposed to antimatter. And it turns out, from the best research and results we have so far, it turns out that it doesn't need to be a huge difference, but if there was a slight difference in the number of antimatter particles versus matter particles, then that's enough to actually cause the universe to be all matter and very little antimatter. But particle antiparticle type depends on temperature and energy, and the higher energy means a particle with greater mass can be created. So if you're in an area where it's high energy, which is what the early universe is, the early universe is everything that exists, all the matter, energy, dark matter, and dark energy existing in something early on, which might be smaller than the nucleus of an atom. That's an extreme version of high energy. That high energy being around spontaneously allows electrons and protons to be generated out of nothingness, and so on and so forth. So any extra energy goes into the kinetic energy of particles, meaning if you have this energy, that energy can spontaneously be used as E equals mc squared to create a mass m. If that energy is greater than 2 mc squared for the electron, the electron has a mass, multiply that by c squared, and then you double that, 2 mc squared. If the energy around is that big, then you have just enough to create an electron and positron at the same time. If you have more than that energy, then you have enough to create an electron and positron at that time, plus give them each a little bit of kinetic energy. So that's what that last line is saying. So the universe was originally full of photons, electrons, and positrons. Those were the first composite particles that came along with the photons and positrons, or excuse me, the photons, or excuse me, I read that as protons, my fault. Those were the first particles to come along with photons, electrons, and positrons, because they are what we think of as elementary particles. They're not made of smaller things, right? You wouldn't have protons until you had quarks and gluons. So quarks and gluons might have been there as well. As the universe cooled, the particles and antiparticles annihilated each other. There were slightly more particles than antiparticles leaving matter after the available particles had annihilated, not antimatter. So that's the research I was talking about. The best research right now suggests it didn't have to be a huge discrepancy between the number of protons and, or excuse me, the number of matter particles versus antimatter particles, but it had to be some difference, and some difference, which we don't know why. I mean, from a statistical standpoint, it seems to me that we should have about the same number, but some kind of symmetry broke, and that did not happen, and that it resulted in us having a matter universe, not an antimatter universe. So there are several ideas to explain why the amounts of matter and antimatter were not equal in the universe. Again, that's not my area of research. I know they have symmetry breaking and all these different ideas that they use to explain it. The times that I've heard them, I've not found them overwhelmingly compelling. But again, I've realized I'm an average person, so maybe I just can't get it or something. I don't know. But just right now, it's still undiscovered or unfulfilled experimentation that needs to be done so that we can solidify the reason. So right now, we really just don't know. But there are a lot of ideas out there. One set of ideas is called the grand unified theories. There's the guts, because they combine electroweak and strong forces into one force in combination with general relativity to explain the physics of the early universe. The guts predict proton decay, but at a very slow rate. So we're not sure that's accurate because protons have never been shown to decay. So if we show that they decay, then we get closer along to believing those guts that predict that. Earlier in the universe, the conditions were extreme. So at 10 to the negative 43rd seconds, that's 0.42 decimal places, and then 1 after that, seconds. After the Big Bang, about 1 with 45 zeros after it, observable universes would have fit in the volume of a proton. So imagine that, just 10 to the negative 43rd seconds after the Big Bang, a 1 with 45 zeros after it, observable universes would have fit into the volume of a proton. That is a seriously small size object, fitting huge things in it at a very early point in the universe. General relativity does not describe space-time under these extreme conditions. General relativity sees space-time as a continuum without, holes in it and weird stuff like that, discontinuities as we call them in mathematics. This era, this very early on, is called the Planck era. You can actually put together the various constants of the universe and such that you get a unit of time. And when you do that, you get a roughly 10 to the negative 43rd seconds. That's the Planck era of time, and it involves, of course, Planck's constant. A theory that combines general relativity and quantum mechanics is known as a theory of everything, or a TOE, as I told you. Physicists are all still searching for TOEs that combines all the 4 fundamental forces. Two popular ideas of this is quantum loop gravity, and another one is string theory. And there's actually versions of each that are, different or nuanced from one another. But in reality, those are sort of our best guesses at what could unify them. But right now, both of them only make predictions that we already know, or they make predictions that we're not yet ready to test. So in some sense, they're not even science because we can't prove them wrong yet. So that's a bit of a problem. So here's a timeline of the universe, if you will, and it's important that you sort of look at this, and you'll see some of the questions in our homework makes you put these things in order because they want you to understand what's going on. So in the Planck era, basically there was a Big Bang. Within the first 10 to the negative 43 seconds, the temperature is 10 to the 32nd power. That's 1 with 32 zeros after it Kelvin. And the density of the universe is 10 with 99 zeros after it, kilograms per cubic meter. That's 1 with 99 zeros after it, times heavier or more dense than water. So that's a really big deal. At that point is when we think inflation occurred. And when inflation occurred, we basically got to a much larger size, but still relatively small compared to the universe today. It's just we went from such a small size rapidly to a very large size in a very small amount of time. You can see even to the gut breaks, that's 10 to the negative 35th second. So this at most could be 10 to the 12th or 10 to the negative 12 seconds. So that's about how much time would have passed between here and here for inflation to occur. And like I said, the universe would have went from, say, the size of a grain of sand to the size of the observable universe is right now. Only it started way smaller. So that's why it didn't become so big. At the gut breaks, this is when the grand unified theory thinks it suggests that gravity and the electroweak force and the strong force, all of those things were one and the same because their energies were so high you couldn't distinguish the carrier particles from one another. At that point, the temperature got low enough that you could start to discern them, and you'd actually get the breaking down, or the gut breaking down into what you see as the weak nuclear force over here and the strong nuclear force over there. Later on, you see that the electron-positron pair annihilation occurs. Then we have the energy being so high that the Big Bang can produce the other elements other than hydrogen and helium, which really just is lithium, beryllium, and boron. That's the latest elements I've seen that they think came out of the Big Bang. Again, just in trace amounts. Then around 3 minutes after, we get recombination. So 3 minutes after the Big Bang, recombination occurs. That's when basically the energy is low enough where the nuclei of hydrogen and the nuclei of helium can attract the electrons and hold on to them. Because of that, most of the energy that's around, most of the ambient radiation can escape because only certain well-defined wavelengths can be absorbed by hydrogen and helium and trace amounts of lithium, beryllium, and boron. So the rest of the light comes out, and that is the light we see as the cosmic microwave background radiation. So that recombination would have been basically done by around 10 to the 5th years. So basically 100,000 years after the Big Bang. And that's, if we take the scale factor from that time to now, that is what we have to multiply the wavelength of 4,000 Kelvin light by to get the wavelength of the microwave background radiation right now. And that wavelength is consistent with 2.73 Kelvin, which is given by Wien's law. So that's really what happened after the Big Bang as best we can tell. Again, we don't know what caused inflation. We just think that it happened, and there's some experiments supporting it, including experiments regarding dark matter and stuff like that supporting it. But again, that's not completely settled science, or Alan Guth would have already won a Nobel Prize. So matter and photons cooled, the atomic nuclei formed. That was the Big Bang nucleosynthesis. Neutral atoms could form and light streamed out into the universe. That was the recombination and the creation of the CMB, and galaxies and stars could form. So speculative ideas, superstring theory. So one idea for TOE is superstring theory. Elementary particles are viewed as excitations traveling along strings. So what they do is they literally mathematically, let me talk to you looking at you in the face with this one here. So I'm going to stop share for a second. So mathematically, there's a problem with the electron and the photon and other particles that we think are elementary particles, which would be like the quarks and gluons, in that they seem to have no physical dimension. Like everything we've done so far to measure their size tells us that the size is smaller than we can measure, right? That does not mean that it definitely has no size. It just seems that way right now. At one time, it seemed that way about protons, but we now know the proton has a diameter on the order of 10 to the negative 14th meters. But these other things seem to not have any such diameter. But again, that could just be a technological issue. But if that's the case, if there exist particles that are infinitesimal and have no physical dimension, mathematically, that's a real big problem. You have things like general relativity that requires objects to have physical size, and it requires space to not have any holes or gaps in it and stuff like that. So what they do in string theory is they imagine that maybe, just maybe, this thing that looks like it's infinitesimal in our universe is actually not infinitesimal. It actually has a physical dimension, a very, very small one, but that physical dimension is in higher dimensions other than R4. So R4, left, right, in, out, up, down, and then time. Those are their 4 dimensions. But if you imagine there's more dimensions, then you could say the electron is actually represented by a loop, if you will, only where it intersects our space looks infinitesimally small, but in fact it actually has a physical size, but the rest of that ring, if you will, is in higher dimensions. So that's really what the idea of string theory is, and how it helps us is by not claiming that the electron has 0 physical dimensions. There's this process called renormalization that happens when you're working in guts and things like that, where you actually have to do integrals that go to infinity. And in order for you to make sense of them, they can't go to infinity. And when you have division by 0, which is basically the size of an object being 0 is a problem, you're going to divide by that. You're going to actually get a 0 in the denominator. So there's ways called renormalization that you can actually make those infinities go to not infinity. And that string theory allows us to do that by considering higher dimensions where it doesn't go to infinity. So that's sort of a back of the envelope explanation of what I'm talking about here as far as string theory goes. So let me go back to the slide. And Elementary particles are viewed as excitations traveling along strings. One particular excitation of a string could make an electron. Another one could make, say, a gluon or something like that. But different elementary particles are like different notes played on the vibrating loop. So we're seeing these particles as if they're, like I said, little loops. But at the same time, we're saying that those little loops have different frequencies, and those different frequencies could be representative of different particles. Theoretically, these tiny strings are vibrating in a universe with 9 spatial dimensions instead of 3. And that makes space, of course, 10-dimensional. And string theory is not a well-tested theory because there are virtually no tests available given current technology, and a theory must be testable. So we can't yet prove it wrong, right? Well, we could, but we'd be proving a lot of our other science wrong, because right now string theory gets everything that we already know correct. Is that because we made it to be correct with those things? We don't know, but it could be, but it might not be. If it's not, then maybe we are on the right track. But right now, we just can't call it a theory. Even though the theory is right in the name, it's more a string hypothesis. It is no more than an idea that gave direction to theorists. It should be called string idea, or maybe string hypothesis. Another thing that we use is the idea of the multiverse, because it turns out the universe, in order for humans to exist, all these constants have to be perfectly dialed in at exactly what they are, very close to it. The way we can explain that is, imagine that there's a multiverse. There's actually, an infinite number, say, of universes. And the reason we're here is we just happen to be one of the ones where all those numbers were just right. So that's a way you can understand the multiverses. Plus, it helps us with quantum mechanics when we start to see things as being probabilistic. So the multiverse is a hypothesis as well. It's not a theory. If the universe is flat and infinite, containing an infinite number of disjointed universes, observable from unobservable from ours, excuse me. There are several versions of the multiverse idea. There are no currently meaningful tests for any version. One version of the multiverse idea is eternal inflation, a theory suggesting the new Big Bangs are forever forming, creating new bubble universes. This would answer the question of what happened before the Big Bang. But again, this is something that's more of a hypothesis than a theory at that point. So that's it. We're done. And of course, luckily just in time, because the time is up now. I actually ran you over 2 minutes. I think you guys have a test that you have to get to do. Let me double check on that while you're here.
Yeah, it says it's due on the 22nd.
Okay, thank you for that. Yeah, the 22nd. Yeah, you got to test it, because that was actually due on the 19th. I pushed it back. I had noticed a couple of students hadn't gotten it done, so I just pushed it back to the 22nd. Make sure you get that done. That is test. Was it test 5, Rose? Is that what you or?
Yeah, 16 and 17 for
Yeah.
chapters, and then you said we have 19 and 20 that's due on Sunday.
Yes. So
okay, that one's not out. That one's not out yet.
Okay, so that's the one I'm going to put up right now. And y'all can, I should be doing it right now. I'm just going to check, make sure it works. I meant to do it last time, I forgot. So that one's now available. I just made it available. I'm going to check, make sure it actually works. It appears it has, sometimes when you make a test, it actually has the question banks linked, but it don't actually have questions in there. And this seems to have screwed up as well. So let me, so I'm gonna have to fix one question about it, and then that'll work. I'm actually just missing one question this time, so that makes me feel a little better. So yeah, you got that. It's got 19, 20, and this is 19, 20, and 21, by the way. I don't know if that's what my test says. Yeah, the test title only suggests, oh no, it is 1920, my fault. It was 21st century astronomy. That's why I had the number 21 in it. So test 7, covering chapters 19 and 20. I'm going to say that should be due by Wednesday. So any questions on that, folks?
So we have a quiz or a test due tomorrow, but then also there's another test for next week on Wednesday.
Yeah, the test for tomorrow was actually due the day before yesterday, but I just moved it back. So it's not like I gave you a new test. I just gave you an extension on the existing test.
Okay.
Man, don't berate me, dude. No, I'm just playing. So yeah, just make sure you get that done. If you haven't done test 6 already on chapter 17 and 18, make sure you get that done because I've given you an extension for no reason other than I like you goobers. So other than that, you're free to go, everyone. I will stick around in case anybody has questions.
Professor, I don't have a question, but I was just wondering if you could respond to my email.
Is this Amani again?
Yes, it's
I'm
Amani.
actually looking at a different score. I thought I just responded to you once this morning. Let me double check. Yeah, I'll go ahead and reply to you real quick.
Let me see. I do have it pulled up right now in front of me. Let me see.
Okay. I wonder if I wrote it or what. Let's see. Let me see if I can even pull it up yet from here. There.
Okay, so I just refreshed it and I
Let's
see.
see.
And it's
Yeah, I see my reply, but it didn't go. It didn't send. I must not have been connected to the internet last night.
Yeah, I'm about to say because I see my assignment graded, and that's the only.
Gotcha.
That was the only notification I received in my email from you.
Gotcha. I've got one from 8:09 p.m. last night, and
then it's the same thing. I just forwarded it to you again.
Okay, gotcha. Yeah, I'll go ahead and reply to that right after I get offline with you. Okay.
Okay, thank you.
All right. See you, Monty. Sorry about that.
It's okay.
Way to keep me ahead of things.
All right, thank you.
See you, Monty. Bye.
Bye.
Anybody else have any questions? All right, looks like everybody's gone now. Autumn, you still there? Melvin?
I'll see you later.
All right, see you, Autumn. Make you feel better.
I'm working on it.
Yeah, it sounds rough. Melvin, do you have a question, bud?
If Melvin got lost in his mountains.
I think so.